Welcome, calculus. Today we're going to talk about Riemann sums and summation notation or sigma notation. But I'm going to forget about this one because I don't like it. All right, let's begin. That's the warm-up. We'll do it tomorrow. So we got to talk about the basics of integration. I did not start with oohs. Oh, well. So what is integration? And I'm going to give you my words. Actually, type in chat. If I say integration, what's like your one sentence explanation of what it is? Does anyone have an idea of what they would say? You can tell me what you think. But here's the idea as people write things. I got my curve here. The area under the curve. There you go. Exactly. So I got my curve. And when I say curve, it's just the line, the function. Oh, that's right. I can't do the stupid. I hate this tablet. Okay. So this is my function f of x right here. And it doesn't have to be a curve. It can be a straight line. And the idea is that you go from some section A to B or some distance. Instead of finding like derivative is the slope, it's the area under the curve. So it's like all this area. How much stuff is here? I like saying, so area under the curve. My other way of saying this is how much stuff. Stuff. I didn't even spell that right. How much stuff? So you're trying to find out how much area is here. And especially like, you know how to do areas of rectangles and those basic shapes. The idea with in calculus is we might have areas that don't conform to one of those basic shapes. So we can use some calculus to figure out that area under the curve. So that's what it represents. Now, another way to say this, again, I say the amount of stuff. So let's say I did this as a graph and I have my function again. I'm just making it a curve because why not? So it's the amount of stuff. So let's say this is, if we're looking at a graph, usually this axis, we can represent our independent variable. Let's say it's like a time. And then this axis can represent some other value. This is like our stuff. This is like the stuff right here. Okay. And then this is like how much stuff you have at all these different times or something related to that. Well, the idea is that when you integrate this, we're going to remove a time unit. So what do I mean by that? So let's say this bottom unit was hours. And then let's say this was like feet per hour. And let's say I integrated this was from hour 1 to hour 5. And then we had all this area right here. If I integrated between hour 1 and 5, what I'm going to get, so my integration is going to tell me how much feet of stuff. Basically, you know how this is feet per hour? When you integrate, you remove one of the time units. So that's one thing you might want to remember. You integrate, you remove a time unit. Like when you derive, you like add a time unit to the bottom. You integrate, you're going to be removing one. So if this was feet per hour and how much feet per hour you were moving at each of these time periods, you integrate this. This tells you how much feet you moved total. If this was feet per hour squared, the acceleration over this time period, when you integrate this, this is going to get you your velocity or feet per hour, your velocity that you went from 1 to 5. Basically, your velocity at this ending time period, 5. Or how much that velocity grew. That's the idea. It's how much stuff you have, all right? So and I think that might help you with some of the early Khan Academy stuff because they kind of talk about that. So let's talk about Riemann sums. That's what this is about. So the idea is that we can approximate the area under the curve using Riemann sums. And the different ways we teach you this are left, right, middle, and trapezoids. The idea is that, okay, in the normal world, if I had one of these graphs, I am going to make one of these graphs this way. Let's say I had this. And I go, oh, okay, I have this graph right here. And I want to figure out how much area is under the curve from there to like there, right? I could find that area, but what if I don't know that function? What if I want to approximate it? Well, I can approximate it by just drawing a bunch of rectangles under there. So I can do like boxes of, the idea is you drawing a bunch of boxes of rectangles And then you know an area of rectangle is length times width, and you can approximate the curve. So there's different ways we approximate it. So let's say I had points. So I'm going to put the same points here. So I have the point here, here, 3, 4, and 5, right? And I'm going to have those same points for everything, hopefully. I wonder if I can just do that. Oh, sick. No. Did it work? No. Okay, let's say I had these 3 points. Can't just duplicate? Control V. No. Okay. So you got those points for everything right here, right? And let's say I have the points here. And these are like 4 main ways to approximate. There's other ways, but don't worry about this. The first way is left-hand rectangles. And the idea is you're taking the left-hand point and you're making rectangles off of these left-hand points. So the idea, I like drawing this shape like this as a reminder. It's a left-hand rectangle. So my rectangles that I'm going to approximate are based off this left-hand point, and you add up the areas of each of those rectangles. Now, a right-hand rectangle is the idea that you base it off of the height of the right side. So when you're building it, usually you start on the right side. And these are perfectly straight rectangles. Of course they are. Notice I don't do one at the very end. That's okay. Now, and then you add up. Now, obviously, if I add these up, it's not going to be perfect. But we're approximating, right? We have another concept called the midpoint. The midpoint of a rectangle is, let's say I had 3 points. Oh, wait, I don't want to draw it like that. The idea is that you're basing it off of the middle of the rectangle. So the key thing is I need 3 points for midpoints. And these are where it gets kind of weird. You're not just like halvesy of this. What you're doing is you're saying, hey, that's a midpoint of a rectangle that's going this whole distance. So I'm going to build it up like that for my rectangle. And then for this one, I'm going to use that middle one to build my midpoint rectangle. So it could kind of look like that. And then the trapezoidal one. This is the idea that we're building trapezoids. Now, trapezoids, you might say, hey, trapezoids look like this, right? Well, they don't have to look like this. Trapezoids can look like this. They don't have to have 2 angled sides. We're not isosceles trapezoids here. Trapezoids just needs 2 parallel lines. They don't care if they're the same length at all. They don't care how it's oriented. So what we actually do for trapezoidals is we're building sideways trapezoids like this. So you got these 2 parallel lines, and you're going to be building trapezoids like this. So what we do is we connect the 2 points, and we just do a straight line, and we're building that trapezoid. Now, another thing when we're doing trapezoids, I like saying that we're going to be taking the average height. So where the left height was taking, this is taking the left height of the rectangle, and the right is going to be taking the right height. And the midpoint's going to be taking the middle height. The trapezoids, I like thinking of this as taking the average height. All right? Someone try and talk? No. All right. So, and I'll give you an example of what that's going to look like. But think average height, to me, that helps out. All right. So let's say I wanted to figure out this curve. This is going to be like a quick example. Okay. See this shape right here? I just have boom, 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 a few points. How would I actually, now if you had to approximate this right here, and you're looking at home, you're like, well, what's the area under that curve right now? How many blocks is this? If we were in person, I'd be like, pause the video. So go ahead and pause the video right now. All right. How many is it? I'm going to start counting. I'd say 1, 2, 3, 4, 5 blocks. So there's 5 so far. And then this is like, maybe all this adds up to 1 block about. This is like half a block. And maybe this adds up to like 2 more blocks. I'm just guessing right now, and I'd say 6, 7, 8. I'd go 8.5 on my bad guess, right? You're kind of counting up those blocks. Let's see what it really is. Well, let's see. Let's try different approximations. So I'm going to try a left-hand approximation right here. And that means left-hand rectangles. Again, we're going to be basing it off the left-hand height right there. This point right here is actually going to be a flat line. There's nothing. So this rectangle is going to go look like this. And then our next rectangle is going to be off this height. And that's it, because there's nothing left here. We're stopping at 3 spots in, right? So what is my total height with left-hand approximation? It's going to be 0 plus 1 block plus 4 blocks, so 5. That looks like that's going to be a little low. So actually, let's try another one. Let's try a right approximation. So left was 5. So I'm actually going to keep this. So left was 5. Let's try a right-hand approximation. So I'm going to start on the right-hand side. Moving on down, perfectly straight. And then my next block, I'm going to start here. Going to make a perfectly straight rectangle. And then my last one, I'm going to start it right here and make that rectangle. So this is going to be for my right-hand approximation. Again, you're off the right-hand corner. It's going to be 1 plus 4 for this one. And this is 4, 5, 6, 7, 8, 9 for this one. So that's going to equal 14. So I'm going to save that. Right equals 14. All right, let's try a different one. Let's try trapezoidal approximations here, right? So we're going to erase all this. Now, the idea of trapezoidal is I'm going to take these two, I'm just going to take a line straight through them and do this. Now, I like saying average. The height over here, and I can write down the height of each of these. This is at 0, 1, 4, and 9. The height, 0 to 1. What's the average of 0 and 1? You don't know. You're in calculus. Add them and divide by 2 when it's 2 numbers. So it's 1/2. The average of 1 to 4. Okay, is going to be this. What's 1 to 4? That's going to be 2.5 or 5/2. Right? And then for the last one, it's 4 to 9. It's going to do a perfectly straight trapezoid line. So 4 to 9, what's the average? 4 plus 9 is 13 divided by 2. So let's add these up. I'm at 1/2 or 0.5. I'm going to go decimals. Plus 2.5. 13.5 is 7.5. So I'm going to be at 10.5, right? Is that 13.5? Yeah. 7.5. There we go. We have a trapezoidal. It's going to be 10.5. So different approximations. Which one's the best approximation? Probably just eyeballing our graphs, trapezoidal was probably the best. Oh, I could have probably done midpoint too, but that doesn't make sense because there's not enough points. Trapezoidal is probably the best. And my guess is in most cases, it's going to be the most accurate because it kind of smooths out the curve the best. But some are going to overestimate, some are going to underestimate. A lot of this depends on what the curve looks like, all right? So that's what's going on there. Your other teachers might teach you like, hey, look, here's the formula for trapezoidals. I like just adding up the average of the heights. Like, and I'll show you. I'll do the final example. Like, I don't know. If you like this formula, go for it. I hate that. So what happens when the rectangles get smaller, right? If I have a lot of big rectangles, or it's a very wide distance in between each, you probably get a worse approximation. But let's say, so if I did this distance is 2, but then I did 4 rectangles, you see, hey, I probably get a smoother approximation because like this little chunk is gone and this little chunk is gone. And if I doubled the rectangles again, I'd get an even better approximation. Brian showed up. Thank you. So The more rectangles you get, the better your approximation. And if you get so many rectangles, you get to see a website. And I want to show you this website. I will pull it up right here. Hold on. My websites aren't working. Hold on. And here's the website. Oh, I'm sorry. That wasn't the right website. But while I'm here, let me tell you something's happening. This week, we have a fundraising event at John Smith Subs. Come on down. Thursday, 4 to 8, fundraise for the school. Have the best subs in the world. It's your opportunity to meet with your family. Yes. You can clip this. Just clip it when I post this online. All right. I ain't going to edit this out. They were okay. YouTube, they were complaining. Here's the other website, the fake website. So, Riemann Sums are kind of neat. Yeah, I'll put this in chat if you ever want to play with this. Oh, why is it going nuts? So, what's cool about this is like the idea is I can change the number of. What's going on, bro? It's like the idea is, oh, this was working before. Being really weird. Okay, so the idea is that, hey, the more I have, and if I choose one of these different types of graphs, the more rectangles you have, the better the approximation is going to get. Wow, this used to work really well. It would like move this in live time. It's being really weird right now. The idea is the more and more you're going to get a better curve. And guess what? If you get to the point where you have an infinite number of rectangles, that's where you get the actual area under the curve. Because if the width of the rectangles is infinitesimally small, then you are good. That is the length of the rectangles. You know what's not small? Your appetite. Right now. I bet you're getting hungry. You know, you don't have to wait till Thursday, but I would. And by a lot. And you can even sign up for an account and get points to save up for discounts on future subs. I'm going to let you in on a little deal. Go there, and you know, sometimes you get the fries. And you can get Parmesan fries or you can get Cajun. You can ask them to do both. You're welcome. All right. So other parts of calculus. Sometimes we want to know if this is going to overestimate or underestimate. All right. And a lot of that depends. So if you're looking at these graphs right now, this is left, right, and a midpoint. Which one over and underestimate? So obviously this left one's going to be under because everything's smaller. And this right hand is going to be over. This midpoint, that's hard to tell. You can't really tell. It's hard to tell. I mean, I don't know. It might over a little. It might be over. I'm not sure. It'd be slight, but it'd be really close because like this over kind of compensates to that under, right? Kind of cancel each other out. But I think this is more of a left and right thing. Sometimes we want to know, does a left or right graph over or underestimate? Now, here's the question they'll always ask you. What is the first derivative of this curve? F prime. It's increasing, is going to be positive. The second derivative, concavity, it's concave down. Frowny face, so that's going to be negative. So you might see questions on an AP test like, if F prime is positive and F double prime is negative, will left-hand Riemann sum over or underestimate? And you're like, what? But sketch it out and you kind of like play with it. You go, oh, okay, that's what it looks like. So if the first derivative is positive and the second derivative is negative, a left is going to under and a right's going to over. So you might get questions. They love doing that on AP tests. All right, last thing. Wow, got 13 minutes. I'm going to do this is based off a table. So the previous examples, it seems like our x distances were always the same. They don't necessarily have to be the same. And you might get a problem like this to like estimate with Riemann sums, especially when you do like real life problems. A lot of times we just have snapshots of like the volume of water or whatever at certain times, or the rate that water's flowing. So pretend we have snapshots here, and I'm going to actually plot these all. I'm actually going to plot it on the stupid other thing. So how do you do right with negative x-axis? Negative x-axis? Or in y-axis? Yeah. You can. I mean, when you're dealing, is that on Khan Academy where they have negative x-axes? So think about this when we're looking at the distance here. It's just, what is the absolute value of this distance? It's not going to be. So you're not talking about like rectangles would be under the y x-axis, right? You're talking about stuff that'd be on the left side. Okay, I'd have to see what it really looks like, but you're basing off the height and then the width of the rectangle. So it doesn't matter if it's in the negative x-axis. That should be fine. So I'm going to plot these points, 0, 7, 1, 9, 3, 8. Gosh, I gotta get the older version. And this jumps to 8, 9, way over here. And this goes to 9, 7, down here. So all the distances aren't the same, right? And we can even start writing some of this down, like the distance between 0 and 1, that's going to be a distance of 1. And this is going to be a distance of 2. And this is a distance of 5. And this is a distance of 1. So those x widths won't be the same. Now, let's do an approximation of a left-hand Riemann sum. So if I do a left-hand sum, it's going to be based off these left-hand rectangles. It's going to look like this. And then this one's going to go like that. Like perfect, right? Oh, man. Left-hand Riemann sums. Now, let's do these heights. So the way I do the heights, I actually like writing on here too. If I did left-hand Riemann sums, I'd be like, I like doing this weirdly sometimes. Just to like draw. I don't know if I don't draw that picture. I got to like have some kind of visual, right? So the left-hand Riemann sum, I'm basing it off of this left-hand y value. So it's going to be a 7 times the width, and the width is 1. So 7 times 1 plus this one, 9, and the width of this 9 one is 2, plus the next one, the height is 8, which is right here and here. And that width is 5. And then the last one, the height is 9, because it's right here. And the width is 1. So you would add all those up and go 7 plus 18 plus 40 plus 9 is going to be 25, 65, 74. If this was an AP test, would you add this up? Only if you want to have a chance of getting it wrong. If it's an AP test, I would leave just this answer. You do not have to simplify. Unless it's like multiple choice, then you probably would. Don't have to risk getting it wrong. You don't have to do the math. Just leave it like this. Unless you need to use it for the next part of the problem, which happens sometimes. All right, so that was left, right? Or that was left, correct? Now I'm going to do right hand. So right hand, again, you got to have that. So I'm going to start in the right. And it's going to be this rectangle is the first one. And this one's the next one. And then, doesn't that look so confusing with too many drawings on there? Yep. But you can kind of see it where it's going right here. Maybe I should just erase that first. Yeah, maybe I'll erase it. Sure. So let's try that again. So it's a right-hand one. It's going to be based off that. This one's... Oh my gosh, this is awful. It's based off of this. I could have done... I'm not doing lines, no. So right. Let's take this one. Okay, so it's going to be based off of this. And again, my height's for the right. Maybe I do this. Sometimes I want to do this just to remind myself. Don't have to. But my right, I'll start with this side. So this is a length of height of 9 times 1. It doesn't matter. Maybe you start over here. I don't care. This one right here is going to be the height of 8 this time times 2. This one will be a height of 9 times 5. And then this will be the height of 7 times 1. And you can leave it like that or figure out 9 plus 16 plus 45 plus 7 is going to be 25 plus, so 77 I get. All right, midpoint. So left and right, hopefully you could do. The midpoints are weirder right here. I'm actually going to erase everything here just to show you. So I would like drawing on this, the midpoints. I'm just going to look at these. So I like drawing this. So I know, hey, it's this one. Okay. And the width of these is going to be different. The width is going to be 3 right there. And the width here is 3 to 9 is going to be 6. All right. What does that look like up here? Okay, the height, that's my midpoint. I know it's not like truly the midpoint of this, right? It's just the point that's in the middle. So this is like a bad example of doing this, but it's not the best example. Usually like midpoints would have to be like even distances, but yeah. But I'm going to try that. So these are the midpoints right here. This gives you the point, the meaning of all this. So I'm basing it off of these 9s right here. Are they both 9? Oh, yeah. My graphs don't look the same, but oh, well. So it should be 9 times 3 plus a 9 times 6 for my terrible example, which is 27 plus 54, which is 81. But you get it. It's the middle point. I like if you have tables. Again, I like kind of doing this thing. Up to you. Now the trapezoids. This is the part where like, man, if this is in person, there's a lot of students that like don't understand how to do averages. If that's you, it's okay. I've had students before. I say, how do you get the average of like 6 and 8? Oh, okay, 7. Okay. Now, what's the average of 6 and 15? 2 numbers. You can add them, divide by 2. I mean, that might be the best. So it's okay if you don't get it. Happens. You forget basic math and calculus. So what's this look like? All right, trapezoid. So as a trapezoid, kind of doing these shapes. Ooh, those were some of the straightest lines. You're making these kind of trapezoids there. So what's the average between these two? The average height. And the average height over here is going to be, I'd say, 8. Because the 7 and 9 is going to be 8. This one is a 9 to 8. The average is 8.5. This one is actually going 8 to 9. This is also 8.5. And this average is 8. So we're going to do this height here, which is going to be 8 times 1. And then 8.5 times 2 is that distance. Plus an 8.5 times 5. Plus an 8 times 1. The distance of 1. That's better. So what does that add up to? That's 8 plus, that's going to be 17. That's going to be 40 plus 2.5 because 5 times 8 and the 5 times that. And plus 8. You add all that up. That's 25 plus 40 is going to add up to 65 plus 10.5 from those two. So 75.5. Something like that. Oh, my picture blocked that. There. Well, if you were mad that my picture blocked it, just leave you with this image. John Smith subs. Yeah, if you understand this, you can dip. I'm going to dip. So I'm done recording. Maybe I just have this video sit here and record for like 10 hours of John Smith subs. John Smith subs. There's no H. Except in Smith. See you later.